So in this lecture, we will continue studying what we introduced in the previous one. And here I'm investigating the Gibbs Sampler. And I want to study that in the Q coloring model. So remember, in the Q coloring model, we have a set of colors, 1 up to Q. And the configurations are given on a graph. So we have a graph G, whose vertices are V and edges are E. And the state space, which is represented by omega, these are all configurations from S to the power V, such that, well, if you take two vertices which are connected by an edge, they have different color. So this means that eta x, it's different from eta y if x and y are neighbors. So this for all y neighbor to x. So this is our state space. And we want to define a Markov chain whose invariant measure is given by pi, where pi in our example is just the uniform measure over omega. So this is 1 over omega for all eta in omega. And we have seen an easy way in which we can do that, which is called the Gibbs Sampler. So the Gibbs Sampler will consist in an algorithm in 2 steps. We first choose at random a vertex. And then once this vertex V is chosen, we just replace its value by a value which is given pi. So let me remind you that if I have a configuration eta and a vertex x, we define a measure. So this is a probability measure on S. And p eta x of A, so A, it's a color, it's an element of S. So this is equal, well, to the measure of the configuration, which at site x takes the value A, and on the other side takes the value of the configuration eta. So this is E, A, eta, Czech x, where, well, let me complete the definition. So B in S of B eta Czech x. So just to remember the notation, so this is eta, it's a configuration, so it's an element of omega, x, it's a vertex, and we represent it by eta Czech x, the configuration on all the vertices but x, which coincides with y. So this is y for y different from x, and it's not defined if y is different from x. So this configuration eta x, it's an element of, well, let me call it omega x. So these are all configurations of eta belonging to S. Here I'm taking all the vertices minus x. And here, again, such that, let's say, A eta belongs to omega for some A in S. So eta Czech x, it's just the configuration eta in which we removed the site x. So it takes the value eta y at site y for y different from x. And this is a new configuration of omega, which takes the value A at x and the value eta y at y different from x. So this is a probability measure. And with this probability measure, it's the one in which we will change. So we place at site x a new color, which is a color A with probability P eta x of A. Right, so this is the definition of the Gibbs Sampler. And now what I want to do is to compute what is this probability in the case of the Q coloring. So for that, well, this will be, remember, pi, it's the uniform measure. So this will be either 1 over omega if this is an allowed configuration, or 0 if it's not. When is this an allowed configuration? Well, when the color A is an allowed configuration, which means when A is different from eta y for all y which are neighbored from x. So maybe let me define as S eta x all the colors, the neighbor colors. So this is all the colors, so all values of eta y for y neighbor of x. And in some sense, well, this is all the colors which are not allowed, and so this measure, maybe let me define that as the complement of this set. So, or if you wish, let me define S of S as the set S minus all colors which are not allowed. So all eta y for y neighbor of x. So if y is a neighbor of x, eta y is the color at y for the configuration eta. So these are, if I take x, all neighbors of x. So I'm taking the colors of all these vertices. This is the set. And therefore, all these colors are not allowed. And so the color at x can be only one of a color in this set. And therefore, pi, with this notation, it's very easy. Pi eta x of A will be either equal to 1, because I'm dividing, well, okay, let me write it. So suppose that A belongs to S eta x. So A, it's an allowed color. Therefore, this probability is 1 over the cardinality of the set. And here, I'm summing 1 over the cardinality of the set times all possible colors. But the possible colors are just the number of allowed colors, and this is S eta x. Otherwise, it's 0 if A does not belong in the set of the allowed colors. So we have a formula for that. So let me write it here. P eta x of A, it's either 1 over the total number of allowed colors at x for the configuration eta. So this is if A belongs to S eta x, and it's 0 otherwise. And therefore, the algorithm consists in choosing first at random one of the vertices and then updating the value of the color at site x, and with which probability? Well, with this probability. So that's the definition of the Gibbs Sampler, and we have seen that the Gibbs Sampler, it's so that this algorithm, or the Markov chain generated, induced by this probability, it's reversible with respect to the measure pi. So let me now derive the equation for the transition matrix from this equation. So what I want to give you now is to compute the transition probability. So to give a precise formula for the probability that if you are at eta, you jump to psi for the Gibbs Sampler in the case of a Q coloring, the Q coloring model. And just mind that here I'm not excluding A to be equal to eta x. So if A it's equal to eta x, it's clear that A is an allowed color. And well, if I choose here A to be eta x, this means that I'm not jumping. So with a certain probability, I just jump from a configuration eta to the same configuration eta. And that will guarantees the fact that this chain is aperiodic. So now let's compute this probability. And since we have seen that we change only one color at a time, so if the distance between eta and psi is larger or equal to 2, this probability is just 0. So now I have to consider two cases, the case in which the distance is 1 and the case in which the distance is 0. So if the distance is 1, this means that eta and psi are different at only one side. So there exists a site x in V, so a vertex x, such that eta y is equal to psi y for y different from x, and eta x is different from psi x. And in particular, that means that psi is equal to txa of eta for some a. So there exists a color a such that psi is equal to txa eta. So remember that this configuration, it's a new configuration which is obtained from eta by putting color a at x for eta and keeping all the other colors just the same. And of course, since this distance is 1, this means that this a is different from eta x. Otherwise, if a is equal to eta x, that would mean that psi is equal to the configuration eta, and therefore the distance is 0 and not 1. So if the distance is 1, this means that there exists this x, such that psi is equal to this new configuration for some a which is different from eta x. And of course, a, it's an allowed color, so it belongs to this set eta x. And in this case, sorry, what is the probability that you jump from eta to txa eta? Well, first, you have to choose the site x, and this happens with probability 1 over v, because you choose at random the vertex. And then, well, we have seen that you choose the color a with this probability. So this is 1 over s eta x. And of course, this is for all a, such that a belongs to this configuration and a is different from eta x. So this is the transition probability in the case in which the distance is 1. So you may jump from eta to a configuration txa with this probability, and here you're taking all x in the set of vertices in V and all a in the set of allowed colors, which are different from eta x. And, well, this means that you jump from eta to eta with 1 minus this sum. So minus the sum for all x in V of this probability, this is V. And since we have seen that eta x, it's always an allowed color, this gives us 1 over s eta x. And this is mind strictly positive, because here I'm assuming that, well, okay, this is, let me say just for the moment that it's non-negative. So this is the definition of the Gibbs sampler in the case of the Q coloring model. So in this case, so let me resume what we have here. The probability to jump from eta to some txa of eta it's given by 1 over v, 1 over s eta x, and this for all x in v, and for all a, which belongs to s eta x minus eta x. If I want here this configuration to be distinct to that one. And then you have a probability that you jump from eta to eta, which is 1 minus 1 over v, the sum for all x in v of 1 over s eta x. And, well, and this defines, therefore, the Gibbs sampler. And what we have seen, it follows from the general theorem, which I proved in the last lecture, is that this measure pi is reversible for this Markov chain. So for the Markov chain induced by this transition probability. So it's non-zero. The transition probability, it's non-zero only in these two cases, and in these two cases, they are given by this formula. You probably have seen that there is a small mistake here. Here, I'm jumping from this configuration to that one with this probability. So if I want to sum over all configurations which are different from the configuration eta, what I get is that this is this set minus 1. So here, actually, this is s of eta x minus 1, and this probability that I'm jumping from eta to eta is actually given by 1 over v, sum for x in v of 1 over s eta x. So for each x, there is a probability equal to 1 over s of eta x that I choose exactly the same color as before, as I was in. So there is this probability that A will be equal to eta x. So the probability that I jump from eta to eta, it's, well, first I have to choose one vertex, and this happens with probability v. And then, given that I chose this vertex x, the probability that I don't change its color, it's given by 1 over the number of colors, or number of allowed colors. So actually, there is a mistake here. There is no minus here, and this is the probability that at which I jump from eta to eta. And since this is strictly positive, what we get is that not only pi is reversible, but also that pi is aperiodic. And now, in order to be able to use the ergodic theorem for the Markov chain, I need to guarantee that this Markov chain, so this is the Markov chain, that the Markov chain is irreducible, but as I said, this might be a very difficult problem if the total number of colors is very small. But we will see that later in this lecture that if the number of colors is large with respect to some parameters in this model, then it's not that difficult to show that that this model is reducible. So here, this is a model-depending proof. So you have to show that, well, given the graph, given the number of colors, then this Markov chain is irreducible. And if you can show that, you can use your theorem to say that if n is very large, then the distribution of the Markov chain xn is very close to the stationary distribution. And this is the topic of these lectures. Now I want to present you another algorithm, which is called the Metropolis Dynamics. And this is another way in which we can construct Markov chain, which is stationary with respect to a fixed invariant measure. So what we will be thinking is that we have a set omega, And this set omega, it's made of finite number of elements, which I'm representing here by n eta 1 up to eta m. So the example you have to have in mind might be, for example, the hard-core model, in which omega is the subset of 0, 1 to the power v, which is v, it's a set of vertices, and we have a certain restriction such that eta x, eta y has to be equal to 0 for all y neighbor of x. So this is a model. And now, well, I will define in this set, omega, so in this very big set, a set of edges of omega. And I will say that two configuration eta xi belong to this set. Well, if xi is a neighbor of omega, of eta, which means that if there exists an x in the set of vertices such that xi is equal to sigma x of eta. So if I can obtain xi by flipping one side of eta, I will say that xi is a neighbor of eta, and this is equivalent to saying that the distance between eta and xi is 1. So in this way, so remember, we started from a graph. With this graph, we created a set of configurations, omega. And now, note that not only the set of vertices was important in the definition of this set, but also the set of edges, because it's the set of edges which establish the conditions on the configurations, the hard-core conditions. And now, well, given that graph, we constructed this set. And now, once we constructed this set, we can define a new graph whose vertices are now omega and whose edges are all pairs such that the distance between these two configurations is equal to 1. Right? So this is what we have in mind here in defining the Metropolis dynamics. We have a set of configurations, omega, and then we have a set of edges. And given these two objects and a probability measure pi, so pi is a probability measure on omega, I want to define a Markov chain, so a transition matrix P, such that pi is invariant for this Markov chain. And the way in which we will do it is the following. I'll first define the degree of a configuration. So I take a configuration eta, and I represent by d of eta the degree of a configuration, and this is simply the number of neighbors of eta. So this is equal to the number of xi in omega, such that xi is a neighbor of eta. So remember, we have a set of edges, and we'll say that a configuration xi is a neighbor of eta if the pair eta xi belongs to the set of edges. So d of eta is just the degree. So if I represent eta by a point here, eta will have a certain, in this set of omega, will have a certain number of edges which arrive at eta, and the degree consists in just counting the number of edges which reach eta. In this case, there are 6 edges. So in this case, the degree of eta would be 6. So this is the degree of a configuration. And, well, once I defined this degree, I can define the transition probability P of eta xi. So what I will do is I will first, I jump only to neighbors. I'll choose one of the neighbors with equal probability at random. So this accounts for the total number of neighbors. So I choose one of them with equal probability. And then I jump to this new configuration with a certain probability, which is the minimum between d of eta pi of xi, and this is divided by pi of eta d of xi, minimum 1. So the dynamics is as follows. Choose one neighbor at random. Once you choose your neighbor, well, if this quantity it's larger than 1, you jump with probability 1 to that neighbor. If this quantity is smaller than 1, then you jump to that neighbor with this probability. So that defines transition probability P. And to make that for each eta a probability, you say that you jump from eta to eta with 1 minus the sum of these probabilities. So this is d of eta, the sum of all neighbors of eta times this minimum, which I will not write. And you see that this is no negative because this is bounded by 1. So I'm summing over the d eta neighbors. So this is bounded. When I take the sum and divide it by d, this is bounded by 1, and therefore this is non-negative. So this is the definition of the transition probability. And now what I claim is that the measure pi, it's invariant for this Markov chain, for the Markov chain induced by this transition probability. And actually, not only it's invariant, but I claim that pi satisfies the detailed balance condition. So what I need to prove is that for all eta xi, pi of eta, probability of jumping from eta to xi, it's equal to pi of xi, the probability to jump from xi to eta. So let's prove this identity, and this I want for all eta xi in omega. So let me write what is, well, of course, if eta and xi are not neighbors, this probability is 0. If eta is equal to xi, this is obvious. So I really only need to check this identity if xi is a neighbor of eta, which means that eta is a neighbor of xi. So then let's see what is the definition. This is these probabilities of jumping from eta to xi. It's given by this quantity. D eta psi pi xi pi eta d xi 1. And now you see that I'm multiplying pi eta d eta by this minimum. So this is, so that expression is equal to this one, and this expression I can put inside this ratio, and when I put it inside, you see that pi d will simplify, and what I get here is that this is pi xi d xi and pi eta d eta. And this is a symmetric expression in terms of eta and xi, and therefore this is also equal to pi xi times the probability to jump from xi to eta, and therefore the detailed balance conditions are proved, which means that pi is indeed an invariant measure for these dynamics, for this transition matrix. So this is the first step. Now we have to check if pi is irreducible and if it is, well, if this chain is irreducible, and if this chain is aperiodic. Mind that, of course, here I'm assuming that this set has no isolated point. So every eta, it has at least one edge, otherwise this is not defined, so the degree would be 0. So of course here I'm assuming that in these, the set of omegas and the set of edges in omega defines a connected set. There are no isolated points, so each configuration eta has an edge starting from eta, or at least an edge starting from eta, otherwise this is not well defined. So now let me show that this chain is irreducible. And for that, remember, I'm assuming that omega E omega, it's a connected graph, which means that if I consider two configurations, eta and xi, well, these two configurations, well, I have a set of edges which goes from one configuration to the other configuration. And so if the set is connected, this path exists, and you see that I'm always allowed to jump from one configuration to a neighbor configuration. So I'm always allowed to jump from eta to xi1 to xi2, and so on, up to the end, and therefore, indeed, if this graph is connected, the chain is irreducible. Now, let's show that the chain is aperiodic. And here I will have to assume that pi of eta of d of eta is not constant. So I have two cases. Either this is equal to a constant, and which means that, let me call this constant 1 over z. So that will mean, so what I'm assuming, I'm considering two cases, right? Let me make it very precise. Either this is constant, or this is pi over eta, d of eta, it's not constant. If it's constant, so let me first consider the case in which it's constant, and then I will prove that if it's not constant, then the chain is irreducible. So if pi divided by d, the degree, it's constant, this means that, let me call this constant 1 over z, as I said. That would mean that pi of eta is just equal to the measure which is proportional to the degree. So that will be the case. So if this is the case, let's go back to the definition of the Metropolis Dynamics. So in this case, as you see, if pi over d is constant, this means that here I have a number divided by the same number, which means that this expression is 1, therefore the minimum is 1, and therefore in this case pi of eta xi will be 1 over d for all eta. So in this case, so let's say case 1. In case 1, the dynamics would be, well, pi of eta xi, it's equal to 1 over d of eta for all eta in omega. And in this case, this minimum is 1, so you see that this sum is equal to d, that will be divided, so p of eta will be 0. And so that's very easy to understand which dynamic is that. If you're at eta, you have a certain number of neighbors, well, you just choose one of them at random and you jump. So that would be a random walk that starting from a point, you jump to any neighbor with equal probability, which means with uniform probability. Of course, this chain might not be periodic. Take the simplest case in which you have only two configurations related by an edge. So that means that when you are at eta, you jump with probability 1 to psi, and at psi, you'll jump with probability 1 to eta, and of course, this chain is not aperiodic. But there is a very simple way in which you can turn this chain into an aperiodic chain, is just saying, well, I will jump, so let me change the dynamics in the case in which the measure pi, it's d divided by z. In this case, we have seen that the Metropolis Dynamics give us this transition probability. Well, let me just say that p of eta, it's equal to 1/2. And you jump. First, you decided to jump or not to jump with probability 1/2. So with probability 1/2, you stay where you are. With probability 1/2, you decided to jump, and then you choose with equal probability one of your neighbors. So that will be a modification of these dynamics, which would say, well, you may jump, you may stay where you are with probability 1/2, and with probability 1/2 you decide to jump, and in this case you choose one of your neighbors with equal probability. So that would give you a strict positive probability to stay at the configuration where you started from, which means that the chain is aperiodic. And I leave it to you as an exercise to show that pi, in this case, satisfy the detailed balance condition. Nothing changed because we are just multiplying all transition probability by the same factor. So the same computation we did shows that pi satisfies the detailed balance condition. So this is what we need to do to get an aperiodic chain in the case C1, in the case in which these ratios are constant. Now, what I claim is that if the ratios are not constant, then then I claim that the chain is irreducible. And if the chains are not constant, well, here I just want to make, so what I claim is that there exists a configuration eta and a configuration psi such that this ratio it's smaller than 1. So I want d of eta over pi of eta to be smaller than d psi over pi psi. So I want to show that there exist two configurations, eta and psi, which are neighbors, and such that this inequality holds. And that's clear because let's say that, well, there is a finite number of configuration. So this quantity here takes a minimum value. Say that the minimum value of this quantity it's equal to some alpha. So choose a configuration eta which attains this minimum value. So here it's a configuration eta and eta 0, say, and d of eta 0 divided by pi of eta 0, it's equal to alpha, which is the minimum value. The minimum of d zeta divided by pi of zeta. Fine. So you start from this configuration, you look at all its neighbors. Well, either there is one neighbor whose value of the ratio is different, in which case you obtained a configuration eta and psi which are neighbors and satisfy this inequality, or they are all equal to alpha. If they are all equal to alpha, now you get the neighbors of this configuration and you start exploring your set omega in this way. And since this is not constant, and since the graph is connected, at some point you will find a configuration here in which the value is strictly larger than alpha. So all inside this connected graph, every value is alpha, but at this point it's not alpha. and here you obtained your pair alpha and something larger than alpha. So this proves that indeed I can always find a configuration eta and a configuration xi, which are neighbors, and such that d eta divided by pi of eta, it's strictly smaller than d xi divided by pi of xi. So there exists this configuration. If there exists this configuration, this tells us that this quantity here, it's strictly smaller than 1. Say it's equal to alpha, which is strictly smaller than 1. And therefore, you will jump from eta to xi with 1 over d times alpha. And this will tell you that when I take the minimum here, there is one term, which is alpha, which is strictly smaller than 1. And that will guarantee that the probability to jump from eta to eta, it's strictly positive. Because for this to be 0, we need this minimum to be equal to 1 for all terms. But there is one term whose value is alpha, which is strictly less than 1. And therefore, this difference will be strictly positive, and that will guarantee, therefore, that the chain is aperiodic. So this proves that the Metropolis Dynamics give you also a way in which you can define transition probability P, a transition matrix, or a Markov chain Xn, for which pi, it's invariant, it's actually reversible, it satisfies the detailed balance conditions. It is connected if the graph is connected, and the chain is aperiodic in all cases. In one case, in the case in which pi divided by d is constant, well, you need to modify slightly the dynamics in order to get an aperiodic chain. But therefore, you have all ingredients you need in order to apply the theorem, which tells you that if I take n very large, then the distribution of xn is very close to the stationary distribution. And this is, as I said, what we are interested in. We want to define these chains and now investigate, well, how large I need to take n in order for this distribution to be very close to pi. So before we proceed, let me just introduce another way, modification of the Gibbs Sampler. So that I will call the cyclic Gibbs Sampler. So we started from a graph, VE, and I proposed an algorithm which consisted in first to choose at random a vertex, and then to modify according to some rule. Modify eta x, eta v, according to some rule, which I will not specify not now, but which you certainly remember. So what we can do, instead of choosing at random this vertex, is order this vertex. So say that the set V, it's equal to V1, V2, up to Vn, where n would be the total number of vertices. And instead of picking one at random, we can say that, well, at time 1, I will change vertex V1, the value of the vertex V1. At time 2, the vertex V2. At time n, the vertex Vn. Then at time n plus 1, the vertex V1, and so on. So this is why I'm calling that the cyclic Gibbs Sampler. So at time 1, change eta x to a with the probability that we have seen, which is p eta x. And I'm sorry, this is not x, but it's v1 in my notation. Then at time 2, you change eta v2 to a certain a2 with probability eta v2. And you do that until time n, you change eta vn. You update the value of eta vn, and this with certain probability eta Vn. And what is the advantage of this cyclic Gibbs sampler with respect to the original Gibbs sampler is that, well, you know that after n steps, you are sure that you modified, well, at least you try to modify the values of all vertices. If you choose them randomly, well, there is a, well, of course, after time n, with a very large probability, if n is large, you didn't update all vertices. Of course, you have estimated saying that, well, after time theta n, there is a large probability, if theta is large, that I updated all. Well, with this new way of doing, you're sure that after time n, you updated or you tried to update them all. And this can be, we'll see that this has some advantage. And of course, after you reach time n, you start it again. So at time n plus 1, you update time v1, you update vertex v1. At time 2n, you update vertex n, which means that at time j plus qn, you are updating the vertex vj. And so you follow the same rule of updating. And what I claim is that in this case, pi is still a stationary state, or still satisfies the detailed balance condition. Mind that this chain is not homogeneous anymore. It's an inhomogeneous chain. So there are transition matrices which are different. So you are using a transition matrix pk to update at time k. So this pk, so let's say that p, as I wrote, g plus qn of eta xi, it's equal to p j eta xi. Here k takes value from 1 up to n, and this transition matrix is the one you use to update the chain at times k plus qn. This is exactly what I'm writing here. If you want to update, this is what I want to express here. If you want to update at time t equal to j plus qn, what you do is that you use this matrix. And what I claim that you can, well, I hope the definition is quite clear, right? You have n different transition matrices. Each one corresponds to the fact that you are updating one special vertex at a time. I will not give you the precise formula for pk here. I'm sure you can write it down yourself. But what I want to stress is that pi, so remember this definition relies on probability measure pi. What I claim is that pi satisfies the detailed balance for pk, for each k. So p eta, pk eta xi, it's equal to p pi xi, pk xi eta, and this for all k and all eta xi. And it follows from this relation that pi, it's indeed stationary for this inhomogeneous Markov chain. And therefore, again, it's the same argument we gave to show that it's irreducible, shows that this chain, it's aperiodic, it's aperiodic, and irreducibility you have to check model by model. So as before, for the Gibbs sampler, we couldn't prove in general that the Gibbs sampler is irreducible. You have to check it model by model. But what's important is that pi is stationary. It's always stationary. And it's aperiodic. And the chain, it's aperiodic. Because there is a positive probability that you remain where you are. and this guarantees that the chain is aperiodic. And irreducible, you have to check it model by model. So this is a third. So we have seen up to now essentially two, but let's say three forms of constructing a Markov chain. The first one was the Gibbs Sampler, the second one the Metropolis Dynamics, and now we have seen a modification of the Gibbs Sampler, which I'm calling the Cyclic Gibbs Sampler, which will be used in the next lecture in order to show that, to estimate the speed at which you converge to equilibrium, to the stationary measure. And so that completes, let's say, a first part of this lecture in which we define the problem. We have a measure, and we want to approximate this measure. We propose a strategy. The strategy consists in constructing a Markov chain whose stationary state is the measure we want to sample. I propose three ways. Now we can turn to the main problem, but before turning to the main problem, which is to estimate the distance or the difference in the distribution of xn and pi, I want to estimate this distance, or how far is the distribution of xn with respect to pi. Before doing that, I will construct a Markov chain, so saying that you gave me a transition probability p, and I have uniform independent random variables uniformly distributed in 0, 1. How do I construct a Markov chain? So this is, I mentioned in the first lecture, so I want to make sure that you know how to construct a Markov chain with these random variables, and then I will start to examine this problem. So, and for that, what I will do is construct a distance between measures, and then I will start to evaluate what is the distance between the distribution at time n and the invariant measure of a Markov chain. So let me consider the question of simulating a Markov chain. So we have a space omega, so this is a finite state space. And on omega, I have a transition probability, and I have a measure, mu. So mu, it's the initial measure, and this defines a Markov chain. So I have a Markov chain such that the distribution of x0, so let's represent by eta and xi the elements of omega. So the probability that x0 is equal to eta, it's given by mu of eta, and the probability that I jump, I'm considering that this chain is homogeneous, so the probability that at time xn plus 1 I'm at xi, given that at time n I'm at eta, this is p of eta xi. And now what I have is that I have a family u0, u1, and so on. These are IID random variables, and uj has a uniform distribution in the interval 0, 1. And I want, with these random variables, with this set, with this family of IID random variable, construct this Markov chain. So I have to first simulate mu, and then I have to, to define these xn in terms as a function of these random variables. You'll see how I will do it. So first, I will define, let's say that we will enumerate all the elements of omega. So omega will be, say, eta 1, eta 2, up to eta n. So n will be the total number of configurations of omega. And I will define a function psi from 0, 1 to omega. And this psi will help me with the random variable u0 to simulate mu. And how I do that? Well, let me define by m of k the sum from 1 up to k of mu eta j. Right? So this is the measure of the set eta 1 up to eta k under mu. And psi of 0, 1 will be psi of x will be equal, well, on the interval mk minus 1 mk. Let's say that k, it's running from 1 up to n, and I will define m0 to be 0. So remember, chi is the indicator function, so chi it's equal to 1, chi of x it's equal to 1 if x belongs to this interval, and it's 0 otherwise. So if x belongs to this interval, psi, which is a function from 0, 1 to omega, will be eta k. So if x belongs to this interval, then psi of x will be equal to eta k. And what I claim is that the probability that phi of u0, so you see that, well, psi it's not defined at 0. You can define it how you want, how you wish at 0, because the probability that u0 is equal to 0, it's 0. So I don't care. But otherwise you define it as you wish. So you can define psi of 0 to be eta 1. That won't change anything in what follows. So what I claim is that the probability that psi of u0 is equal to eta k, that this is equal to mu k, and k from 1 up to n. So by using this function psi and the random variable u0, I can obtain a measure, a distribution, which coincides with mu. And so let's check that this identity holds. Let's look at here. When is psi of u0 equal to k? So maybe, since I'm using the same letter, let me put it j. So what is the probability that psi of u0 is equal to eta j? Well, for this to be equal to eta j, I need u0 to belong to this interval. So this is equal to the probability that u0 is larger than mj minus 1 and smaller than mj. And since u0 is uniformly distributed, and since mj belongs to 0 and 1, and it's an increasing sequence, mind that maybe mk is equal to mk plus 1. If mu of eta k is 0, this means that mk is equal to mk minus 1. So these two values might be equal, but in any case, the probability that u0 belongs to this interval, it's mj minus mj minus 1. And by definition of mj, this is mu of eta j. And this is exactly what we want. So indeed, by using this function psi and the random variable u0, we can simulate the measure mu on omega. So this is the first step. Now let me use the other random variables in order to simulate the transition probability. And for that, I will repeat the same idea. So I will define now a new family which is phi of eta. So for each eta, or let's say in omega, I will define a function phi of eta. And this phi of eta, again, goes from 0, 1 to omega. And phi of eta of psi, I want that to be close to be equal to p eta psi for all psi in omega. So since psi mimic the measure mu, now I want phi eta to mimic the measure p eta. So I'll just repeat exactly the same procedure. So I will define m eta k as the sum from 1 up to k of p eta psi j, or eta j, now define phi eta of x to be the sum for k from 1 up to n of m in the interval m eta k m eta minus 1 k of x, that will be psi of k. So psi phi of eta, it's a function from the interval 0, 1 to omega. And mind that again I have a problem at 0, but let's say that this function is actually defined in this interval. And what now, so phi of eta is completely defined. And now what I claim is that the probability that phi of eta u1 or u0 to be equal to psi k, that this is equal to p eta psi k. And this is exactly the same computation. So keep in mind these two identities which I proved, because now I will define the chain. So with these functions and these measures, I'm now able to define the chain. So x0 will be equal to psi of u0. And we have seen that with this definition, the probability that x0 is equal to eta, this is exactly equal to mu of eta. And this is exactly what I wanted. Now this defines x0. I want to define xn for all n, so I will do that by induction. And I will define xn plus 1 as phi xn un plus 1. So this is another way in which I'm writing phi xn un plus 1. So remember, for each eta, I defined the function phi of eta, and this function phi of eta was defined in the interval 0, 1. So this is exactly well defined, because for xn, by induction, here I constructed x0, it's an element of omega, and now un, it's an element of the interval 0, 1, so this is well defined. And what I claim, so this defines by induction, you have here x0, with this equation you define x1 from x0 and u1, and you iterate that, you have defined the sequence xn. And what I claim is that this sequence xn, it's a Markov chain whose transition probability is exactly even by p. So let's prove this claim. And what I need to compute, it is what is the probability that xn plus 1, so to show that this object, it's indeed a Markov chain, what I need to show, to compute, it's what is the probability that xn plus 1, it's equal to some configuration eta n plus 1, given that x0 it's equal to eta 0, x1 it's equal to eta 1, up to xn it's equal to eta n. So first, I want you to observe that x0 it's a function of u0. Now, by this equation, you get that x1 it's a function of x0 u1, but x0 it's a function of u0. So this means that x1 it's a function of u0 and u1. So if you give me the values of u0 and u1, I know exactly how much is the value of x1. Right? Because with the value of u0, I compute x0, and with the value of x0, I compute, and the value of u1, I compute x1. And similarly, if I take now n equal to 1, x2, it's a function of x1 and u2. x1, it's a function of u0 and u1. So this means that x2, it's a function of u0, u1, u2. And if you, now you see that you can show by induction that actually xn, it's a function of u0, u1, up to un. So that's fine. Let's see. So let's show what I want to prove is that this is equal. In order to show that xn it's a Markov chain, I need to prove that this is equal to the probability that I'm jumping from eta n to eta n plus 1. Right here, I fixed a sequence of configurations, and I need to show that this probability, it's actually this conditional probability, it's actually given by that. Fine, but what, so let's compute this probability. You see that xn plus 1, the definition of xn plus 1 is given here. So this is equal to what is the probability that phi, let me use that notation, that xn of un plus 1, it's equal to eta n plus 1, given x0 equal to eta 0, xn equal to eta n. That's nice. But now I know that xn is equal to eta n. So I can replace this xn by eta n. So this is the probability that phi of eta n, which is a configuration of un plus 1, it's equal to eta n plus 1, given all this expression. That's very nice, because now what is left here, so eta n plus 1, it's a configuration, it's fixed, it's deterministic. Eta n, it's a configuration, it's deterministic. And this is a random variable, un plus 1. So the event here depends only on the random variable un plus 1. On the other hand, x0, x1, xn are functions of u0, u1 up to un. And this sequence, it's a sequence of independent random variables. In particular, un plus 1, it's independent from u0, u1, u2, un, and therefore it's independent of these random variables, x0, x1, xn, because they are functions of these random variables. And since un plus 1 it's independent, we know that this conditional probability it's actually equal to the probability that phi of eta n of un plus 1 it's equal to eta n plus 1. And we computed this probability. So this probability this is the way in which we compute the probability p of eta n. So this probability it's equal to of eta n. So this is the way phi of eta n is the way in which you approximate this measure. So this means that this is equal to the probability that you jump from eta n to eta n plus 1. And this is exactly what we wanted to prove. So I've just shown you how to construct a Markov chain from a sequence of IID random variable uniformly distributed in the interval 0, 1. And by assuming that your computer is able to simulate these random variables, then you can run in your computer any Markov chain on a finite state space by just doing what I presented here in the last 10 minutes. So now that we know how to simulate a Markov chain, we can start investigating the distance between the distribution of a Markov chain at time n and its stationary state pi. And for that, I will introduce, so this is the final topic of this lecture, the total variation distance. So say that we have a finite state space omega, and we have two measures, two probability measures, mu and nu defined on omega. By the total variation, so the definition of the total variation distance between mu and nu, and this will be represented by TV for total variation. So this is just, well, the supremum over all subsets A of omega of mu A minus nu A. So that's the definition. Now, my first claim. Of course, mu A, you can rewrite that as the sum of all x in A of mu x minus nu x. And you want to make that as large as possible. If I want to make the absolute value of this expression as large as possible, this means that I want to make it as positive as possible or as negative as possible. So think it as you want to make this difference, this sum, as large as possible, which means that, well, I will choose a set A here with all points x such that mu x, it's larger than nu x, because this difference will be positive, and if I place, so if I call A plus the set of points x in omega such that mu of x, it's larger than nu of x, if I start with a point in this set, this sum will increase each time I add a point in A plus, and it will decrease each time I add a point which is not in A plus. So the best possible way in which I can make that positive is to choose all points in A plus. So this is the best possible choice to make that large. And to make that small, which means with a negative sign, would mean to take, well, this positive, and so this is the largest positive value which this sum can assume, and the largest negative value which this sum can assume will be x in A minus, for the same reason. Right? But now you see that here, A minus will be, of course, defined as with the other sign, the other inequality. But of course, if I take the intersection A0, which is A plus intersection A minus, well, there is no difference because of taking A plus or taking A plus minus A0, because in A0 these two values coincide. So taking A0, A minus, or A minus minus A0 is the same thing. And since now, if I look at this expression, since mu it's a probability measure, this sum it's equal to 1 minus the sum in the complement of this set, but the complement of this set is A plus. And the same thing here. So you see here I have a minus sign, so that will give you a minus plus x in A plus of new x. The minus 1 will cancel, so that will give me and so you see that this value is equal to that one with a minus sign. So the maximum positive value coincides with the maximum negative value, and it's attained at this set. So this is also equal to the sum of x in A plus of mu x minus nu x. And well, since we are in A plus, I can put the absolute value here inside. And actually, we have seen that this is also, the same reasoning tells me that this is also the sum in x in A minus of mu x minus nu x. This is exactly what I've shown here. And since A, well, and of course I can take here A minus or A minus minus A0, it's the same thing, because on A0 this difference is equal to 0. Now these two expressions are equal, and A plus union A minus minus A0 is the old set. So this shows, and my first claim is this one, is that this is actually equal to 1/2 the sum for all x in omega of mu x minus nu x. So we just proved that this identity holds, right? So by examining the maximum positive value of this quantity and the maximum negative value of this quantity, we reached the conclusion that the maximum value is equal to the maximum negative value, and from that we concluded that this is equal to that, which is equal to that, and therefore this identity holds. So we have a definition and a first lemma, which tells us that, well, it's easy to compute. The total variation between two measures is just summing the difference, the absolute value of the difference of the measures. So this is a first claim. Now, I have a second claim, also a very easy claim. My second claim take two measures, two probability measures. Take the measure you obtained after one step of a Markov chain. And what I claim is that the total variation distance only decreases. So the total variation at time 1, if you start from mu and nu, it's bounded by the total variation at time 0 between nu and nu. So let me prove this claim, but actually we'll prove much more by using coupling. So let me prove this claim. We have seen a formula, so I know that this total variation is equal to 1/2 of the sum. I'm now representing by x the elements of omega, but well, okay, I hope you're not confused by that. So nu p of x minus nu p of x. Now this is equal to 1/2 summation in x, u in our set omega of mu y p y x minus mu y p y x. So I'm putting inside this difference. So now this is of course equal to mu y minus nu y p. And I can bound this quantity by taking here the absolute value. And once I take the absolute value inside the sum, I have a finite sum, so I can change the order, and I will say that this is equal to 1/2. So I'll first sum in x, and then sum in y. And this is new y, p, y, x. And you see, when I sum in x, this gives me 1, and therefore this is equal to 1/2 of the sum over y of mu y minus mu y, and this is the total variation of mu minus mu. So we proved, indeed, that the total variation of mu p minus mu p, it's bounded by the total variation of mu minus nu. Mind that if I take nu equal to pi, nu pi, since if pi is the stationary state, it's equal to pi. So this tells me that mu pi minus mu p minus pi and total variation is bounded by mu minus pi. So it cannot increase. But what we would like is actually to show that this decrease, so maybe we want to put here an alpha and strictly bounded by 1 to say that actually decrease. And if you iterate that expression, you'll see that at time t, that will decrease exponentially fast. So that is what we would like to prove. And this is the distance we will use in order to estimate the, so we'll start a Markov chain at a certain configuration eta. At time n, we will have a new distribution given by the probability that starting at eta time n, we are at xi. We want to compare that with pi of xi, sum over xi. So what we will be doing in this next lecture is to try to estimate the total variation distance between these two distributions by taking here a supremum over all possible configurations of eta. If we can show that this decrease as n increase to infinity, then we will have a bound to say, or a statement which allows you to show, to say that, well, the distribution at time n of this Markov chain starting from any configuration is close to the stationary state. So that will be the goal of this lecture, to obtain bounds on this quantity in terms of n.